Good morning, Randy. Once again, welcome
Hi,
to this
Antoine.
to discuss today reservoir simulation. So maybe a quick intro to today's topic. The issue of reservoir simulation, especially for polymer flooding, is very hot, I would say, in the industry because my personal experience is that everyone I've been talking to has never been able to predict correctly the injectivity or even the recovery and uh, and a lot of other parameters for polymer flooding, which is of course a big issue when you want to design a business case and move to the field, because if the simulation tells you that you will never be able to inject polymer in the first place, the question is how do you convince your manager to move to the field? So there are probably several reasons behind that. We will probably not cover all of them, focus on the polymer. What we can put aside already, which I think is very important, is the model and the geology itself, which is a model is as good as what it contains, I believe, and in terms of knowing your reservoir, which is understanding the perm zones or permeability distribution, porosity, and saturation changes or the status inside the reservoir is already probably something very, very critical to get anything right and moving to the next step of trying to predict anything. So what are your thoughts about this topic to start with?
Yeah, yeah. So I agree with you, and I think injectivity is a very important place to start because that's one of the critical areas where things can go wrong. So first of all, I'm an experimentalist as a general rule, and I've seen lots of simulations over the years, and certainly want to acknowledge, as you suggested, that simulation can be incredibly important, and we need that for quantifying predictions of how much we're going to get out of it. So I don't want to uh, demean the value of simulation, but I think the point of this discussion, this particular period, is to point out some areas where some real mistakes are being made with simulation, very common mistakes that are being made, and some unfortunate assumptions are being put in there that we need to correct. And injectivity is a great place to start because, as you and I have both seen, in fact, we both know there's at least one YouTube video out there where people would make the argument of saying, okay, we've got vertical wells here, and we think we can predict injectivity. And the real question, as you just implied, is are you really able to predict polymer injectivity? And a question that we look at about how the simulators usually go about this. Let's just again say we've got vertical wells we're dealing with. And what I see is that people will say, all right, we know kind of what water injectivity is. We've measured it. And so we're going to, if that doesn't match, a perfect, let's say, a 6-inch diameter or a 1-foot diameter wellbore radius, what we'll do is we'll just expand the radius of our wellbore in our well grid block, okay, so that it matches the water injectivity. And then we'll make our predictions from there. Okay. Well, the problem with that is, and I know that simulations uh, have a real problem um, imitating or simulating the presence of a fracture. And and a lot of people know, my position is all vertical polymer injection wells have fractures or some kind of fracture-like features, and it's critical to realize that, and it's critical to the importance of this. And it's really important to this discussion too, because what the simulators will do, again, as I say, is if they say, well, I can simulate microfracturing or fracturing, what they actually do is they say, well, what I'm going to do is I'm going to continue to assume my wellbore grid block has a radial wellbore in it, and I'm just going to make that wellbore bigger and bigger radially. Well, there's a couple of problems with that. Number one is it doesn't capture the fact that fractures or fracture-like features tend to be very directional. They're going to grow in a particular direction. And they don't capture the fact that that fracture is going to grow. So if I'm injecting water, maybe that fracture is pretty much completely closed and I get one observed injectivity. Now I start injecting polymer. What happens in reality is that fracture grows longer and longer, but that's not captured in the simulation. What the simulation guy has done is he said, well, my wellbore radius is this, and I'm going to keep it fixed at that value forever. So that's why he predicts that when I start injecting polymer, I'm going to get crazy reductions in injectivity. And then they start doing this really flawed argument of saying, I have to therefore, even though my normal mobility ratio calculation would say to get an efficient displacement, I really should have a certain concentration or viscosity of polymer put in, but I have to cut back on that because I'm fearful that I'm going to get, way too low of injectivity and I just won't be able to get the throughput. So it's completely artificial what you're doing in that simulation. The reality in as you kind of implied with your comment, in all polymer injection processes that I've seen in vertical wells, the observed polymer injectivity, maybe not all, but for the vast majority of, is not really all that much lower than water injectivity. And there's only one possible explanation for that, is because during the polymer injection, those fractures extend and make it look like the injectivity is higher than you would have expected if those fractures hadn't grown. And the simulations are not capturing that. So a key thing to remember is that we may be overly artificially pessimistic about injectivity that we get from these simulations, and it has major detrimental consequences. If you're going to predict that I should be injecting a lot lower viscosity than is appropriate for the proper mobility ratio, you might be missing a real opportunity there.
Yeah. But so, because I think when I was discussing injectivity with other people, including Schlumberger in 2019, I was raising the issue of simulation. And so the main problem, I was discussing was the behavior or the profile of the injectivity curve or of the pressure curve. So what I mean is, the first question is, what is an injectivity issue? Because if you look at what should happen in polymer floods is, since normally you are improving sweep and mobilizing an oil bank, at some point, it would be normal to expect a pressure increase or to pressure change, pressurizing the reservoir. Assuming, of course, that, as you mentioned, you don't have dynamic extension or modification of fracture length and all these things which are basically flowing the way we look at the pressure response. So normally I would say expecting or having a pressure increase when you go for polymer is, it's something sensible. The difference I would like to point is, when you look at simulations, the real models, very often what happens is when you switch from water to polymer, the pressure goes to the sky at the moment the person hits the button, or that it goes, the simulation goes into the process of polymer injection, which is basically what I would call a real injectivity issue. But the thing is, at least in my experience, missing probably a few projects, the thing is, I've never seen that anywhere, where basically the minute you start polymer injection, switching from water to polymer, you reach the maximum bottom hole pressure and you have to decrease the rate. I have never seen this in any of the projects I've been looking at. So very often you have a couple of response. You have no injectivity change, injectivity increase, the well going under vacuum or just increasing injectivity. So again, both cases show fracturing. And you have a case where you see, I would say, fill up and then pressure increasing, and then the whole plot is stabilizing. You reach a straight line, and you can continue like this for a very long time. So the problem with predicting injectivity also is, I think, is even worse than that. It's a response in the simulator, which is it's a 0 to 1 answer. It's like I go from water to polymer, and at this very second, I reach bottom hole pressure. And this, if you benchmark against all the literature, I would like to see any case where it ever happened.
Yeah, I would agree with that. Yeah, absolutely. Yeah.
So you mentioned how simulators work, which is so we can go also into maybe the keywords, mathematics, and the equations, and what people like to input into these things. So what are your thoughts about the input, the keywords, and all these aspects?
Well, I don't want to pretend to be an expert on the keywords for the various simulators or experts on that. I just want to focus on the concepts and emphasizing that people, when they use something, knowing what it does. And I suppose that impacts the issue on injectivity of the rheology assumed in the simulator. Now we know that in 100% of the cases, unless you're injecting distilled water, which has never happened, even if you're dealing with something that's only got 500 parts per million total dissolved solids in it, we know that polyacrylamide, whatever concentration you want to use, it's going to show what we call shear thickening behavior at typical near wellbore velocities if there's no such thing as a fracture there, near wellbore vertical well velocities, not horizontal, but vertical well velocities. And if you put in the keyword of saying shear thickening, it would give the response that you said. It would say, look, this shear thickening is going to give me a super high effective viscosity at the velocities right as it enters the wellbore, and it's just going to shut injectivity down right there. That's what your simulator is going to say, unless you've done something really exceptional. And what a lot of people have done, as I've been talking to people myself, and I'm sure you've seen this too, is they say, well, I'm just going to leave off the shear thickening, and I'm going to say it's shear thinning. Okay, so number one, they've made one bad assumption that the polymer is shear thinning. We know that's not true under any realistic circumstance if there's no fracture. And the second assumption they make is that there's no fractures there, so that it's this really limited area associated with the wellbore. So what they've done is they've made two wrong assumptions in hopes that they'll get the right answer on injectivity. And we got a couple of papers out there in the literature where people have done that kind of thing and said, well, I'm trying to match what my real injectivities are. But, that's just, to my mind, it's really tough to get something like that to work because you made two really wrong guesses to begin with, and you're trying to make, subtle degrees of shear thinning that you're going to put in there, and different degrees of maybe of expanding your wellbore, and you don't have any control over them, and they're both wrong answers, wrong assumptions to begin with, so you can't help but get the wrong answer the vast majority of the time. And that's why I'm again push for just assume you've got fracture extension, and you can probably get the proper injectivity that you want. The fear is just, where are those fractures going? Are they cutting out a zone? Are they going too far? Are they doing something bad? That's the real fear. And as you said correctly, in all of these cases, our real actual injectivity is higher than the simulators are ever going to predict. And the question is why? And I think the reason why is because those fractures are extending. And a better question is, when do those fractures extend to the point where it causes me a problem?
Well, the thing is, I think one of the problem we discussed earlier is before choosing the keywords, there is probably a need to understand the near wellbore, the piping, the near wellbore, the perforation, the existence or the absence of fractures. And the easiest way to avoid having problems, for instance, with shear thickening is, yes, if you have fractures, or if you reperforate, or if you enhance your perforations, or if you create controlled, fractures, then you already have no need to study shear thickening. And the other problem is, well, how will you assess that it will even happen downhole, which is probably even another question, which is, how do I know that what I suspect will happen actually happens? So there are a few problems here where it's just better to get rid of the problem, as you said, by just having controlled fracturing, where you don't need to study a few things. Then for the other things, I think in injectivity, if we go back a little bit, in injectivity calculation, there is something that we do tend to forget, and it's I've never seen it in any simulation. You know that the polymers are used in fracturing as friction reducers. They are used as friction reducers. And so basically what happens is if you are in turbulent regime, if you have polymer, and of course in fracturing it's 300 ppm, but we've seen the same effect in 1500 ppm, so 15 centipoise, 20 centipoise. So for the same injection rate, we gained 50% pressure drop. So basically, we inject the same rate for lower pressure drop, and mathematically, injectivity is the rate divided by the pressure difference between the bottom hole and the reservoir. So even this, is a 50% difference in between polymer and water at the beginning when you fill the pipes in your turbulent regime, which probably you are in vertical wells, which has a huge impact on the first, the first iterations of the calculation of the injectivity. And so very often what happens is if you look at startup of polymer injections, you have two ways to start. It's either you fix the water rate and you increase polymer viscosity, or you fix polymer viscosity and you increase the rate. And when people fix water rate and they increase viscosity, what they see is the pressure drop going down like crazy. So the pressure gauges go down until basically the viscosity is ramped up and the fill-up period has been covered. And so now you start going into a more kind of steady state. And so this is a very first step that we don't see in simulator. And it has a huge impact, at least especially if you have not reached fill-up and you're in turbulent regime. And then you have the keywords. So you mentioned shear thinning, which probably is in the wellbore, perforations or fractures. Shear thickening, as you said, is if you have fractures, you have no shear thickening. And so, of course, then you have other keywords that are difficult to, I would say, to assess, which is, yes, what about retention? And you mentioned also later inaccessible per volume. Some people put kind of decay for polymer viscosity. So polymer should lose some viscosity at some point and these kind of things. So
Yeah, so I think what you're saying is what we really need, the best thing to do in our simulators is to put in things that we know and leave out unrealistic things that we know are not going to happen, right? That would make our simulations a lot more credible. And then so on, going back to the injectivity thing, just to finish it up, and then we can move on to something else, is just, I think maybe a thing to say is just to accept that a lot of these simulators, especially with vertical wells, really don't have the capability of predicting injectivity. And if anything that they do is associated with predicting injectivity, we should be really skeptical of that and maybe put that aside and look at other aspects of the polymer flood before we, make all of our decisions or too many of our decisions based on a predicted injectivity from the simulation.
so what would be your the piece of advice you would give to people who only rely on simulations to try to build a very business case and won't move to the field before making sure that they can, the simulation will tell them that they can do it. So because I know few people in the industry for whom basically a reservoir simulation is the word, basically. And if it tells that you can't inject polymer, then you won't be able to inject polymer.
Well, so I mean, it's two parts. I think you and I have both seen this. When the question is, how are decisions made with respect to should I do a polymer flood or should I not do a polymer flood? And the reality in a lot of the cases is some person or important set of person says one of two things. He either says, I want to do a polymer flood. I think that's a good idea and I want to do it. And he gives his subordinate this thing, simulation, laboratory, whatever it is. And those guys know that this is they know the answer that guy wants to see. Maybe he wants to say, look, I don't want to do a polymer flood because I want to spend this money on someplace else. So give me an excuse not to do a polymer flood. One of those two things. So then the simulation or maybe even a lab study is just contrived to get whatever the answer that guy wants to do. So I mean, there's nothing you can do about that. I think all we can really do is focus on saying if you're serious about using this tool, say a simulator, to get what we need to be doing is putting the right physics, the right things into that simulator so that, yeah, of course, there's lots of uncertainty, but at least we damp down the places where there isn't uncertainty. So
Yeah.
that's all I
And,
can suggest.
and so for given the complexity also, because some simulators more and more, there are so many things you could change to try to match the pressure drop you have in the well. How do you know you can play on the viscosity, the shear thinning, the shear thickening, the retention, the grid block size, the existence of perforation, the skin negative skin
Right.
positive.
Good
Then it
point.
can be, yeah, it can be water quality. It can be even the mathematics used in these kind of things. So what I
There's
have
a,
also, yeah,
go ahead.
what I have also rarely seen in the literature is, so history matching is the way many people go, which is I'm trying to match the past with my actual knowledge and tweaking around parameters. The question, of course, is are those the same, which is which one do I change and why? And so given the complexity of things already in polymer, what I have never seen, or I mean, I don't think I've seen that in the literature, is why not start to try to predict the pressure drop in a core flood using the most basic parameters? Like we take a 1 Darcy bentimer, very homogeneous, fully water saturated. We take the rheology information that we have in the lab, and before we run the core flood, we try to predict the pressure drop in the core flood. And then we see the actual results of the core flood and try to understand what's the minimum number of parameters that we have to change and why, to try not to match, but to predict basically what would happen. Because when you run water flood into water injection into a core flood, if you double the rate, you double the pressure drop. It's Darcy's law. So the equations work. I mean, like we can predict what will be the pressure drop in the core flood with Darcy's law and the simple fluid or kind of simple fluid like water. That's how we calculate permeabilities, and it works. So the question is, why not do the same thing and say, look, we think we have equations for polymer propagation, whatever they are, and so we try to predict in the most simple setting what could be the pressure drop before trying to upscale into a much more complex environment where we have way more uncertainties. Because if we can't get, I believe, the basic or the basics right in the very simple model, I think it will be extremely challenging to even, I mean, do anything at the scale of a field or a reservoir, even just a well, given the complexity of things and the things we don't know and don't understand. So
Yeah. Yeah. Um, so along that line, I mean, most people are looking for something fairly simple of just a starting point of should I do a polymer flood or should I not do a polymer flood? And, I mean, it comes down to something fairly simple. You think, I've got a really viscous oil here, and if I can start trying to displace that with water, it's not going to be a good displacement. So, I mean, that immediately says, okay, a polymer flood should be a good option here, unless there's something else that comes in the way that stops it. And a critical question in that, and it gets along the lines of what you were saying with the core fluid, is what's the right polymer concentration or viscosity to be injecting? And we've made some real mistakes in our simulators on that issue. And I think there's, just with a little bit of really good laboratory work, you can answer that one, which I think is kind of your point. Like I was going to mention, we know that if we try, my overall point here is that having a really good feel for what your relative permeabilities, especially your endpoint permeability to water is really very important in polymer flood, because that determines, you know, how much polymer, what polymer viscosity and concentration I'd be injecting. And that's critically economically, right? Critical economically. You don't want to be injecting too much. You don't want to be injecting too little. And the question is, well, how do I determine the relative permeability? I know that's a darn difficult thing to do when I'm injecting water, because I've got an unfavorable displacement, and maybe it's going to take me forever to get me my relative permeability curves. And we have a way around that. And I want to mention this paper, SPE paper 190321. And basically what we do in that paper, that's 190321, is we determine recovery values using a number of different polymer viscosities. I mean, we'll do one core flood with just water and we'll get our recovery curve. And then we'll do another one with maybe 5 centipoise polymer, another one with 15 centipoise polymer, another with 25 centipoise polymer, another with 50 or 100 or 200 centipoise. And we'll, at some point, we'll see that we aren't getting any better displacement, like, for example, at Cactus Lake. We didn't see any better displacement with 100 or 200 centipoise polymer than we did with 25 centipoise polymer. And that tells us that the endpoint relative permeability for that case is like about 0.03. And we would never have known that unless we had done this experiment. And that gets to a flaw that a lot of people are doing in these simulators. They're saying, well, I think a reasonable endpoint relative permeability is somewhere between 0.1 and 0.3, but they don't know it. They're just guessing it because they think that's reasonable, and they put in some kind of curve like that. And then they can't, I've seen cases like this, that they can't get a decent history match unless they do really screwy assumptions with the polymer. Like in one case, they had to do just completely unrealistic assumptions about polymer retention and propagation is the way they would want to go. And the simple answer was to say, let's get the right relative permeability curves, and that solves a lot of your problems first. So it comes down to, I know, as you said, people just want to go directly to simulation, and they don't want to waste any money on laboratory experiments. But here's a case where doing a little bit of good laboratory work has massive importance to you in getting the right polymer viscosity to be injecting. So I think that's something that's really missing from a lot of these simulations, that, you know, they're not being realistic about the relative permeability curves that they're putting into these things sometimes.
So relperm is one, and what about, because what I see also very much in simulation, which has always struck me a little, is the use of rheology curves, but viscosity versus concentration. Which, if I just take one counterexample, if you take associative or thermoassociative polymers, they can have the same viscosity curve versus concentration than any other polymer, but the resistance factor inside the rock can be 5, 10 or 20 times higher in the same permeability and the same apparent viscosity than a conventional polymer. So it's always something that struck me also, is the use of basic viscosity curves versus resistance factors. And so what do you think should be used for resistance factor or viscosity in that case to have something that's much closer to reality than the basic rheology curves?
So I have to separate this into two areas. One is just like using conventional polyacrylamides or ATBS acrylamide copolymer type things. And then the other is to go to more exotic polymer like the associated polymer. So let me focus first on the conventional polymers, because that's where, 99% of the actual activity in the world really is. Okay. So, there's another flaw I see in some of the simulators that are like shown on YouTube, is assumptions of unrealistically high resistance factors. Now, I know you said we're talking about associated polymers, we might see legitimately really high resistance factors, but I want to focus on the polyacrylamide type of case here to begin with. So for the polyacrylamide case, Guillaume Dupois had recently put out a paper where he was showing the actual resistance factors relative to the base viscosity you would expect, and he typically gets a value that the resistance factor is maybe on average about 1.3 times greater than the actual polymer viscosity, and I think that's consistent with my experience also. And I would say if you're dealing with normal polyacrylamide, normal polymers, the way you should look at this is you should never in your simulator allow your resistance factor to be more than twice your viscosity measurement. Okay. And the conservative thing to do is just assume that your resistance factor is going to be your viscosity. That's probably going to be overly pessimistic. And maybe, as Guillaume had indicated in his work, maybe the right value is the resistance factor is going to be about 1.3 times greater than the viscosity. But, so I mean, it depends on whether you want to be conservative or liberal. But making your polymer viscosity more than twice, or the resistance factor more than twice your viscosity, is being too optimistic, too liberal. So that's an assumption I think that needs to go into this.
Just a question on this one. So, and you think that when you correct for the Darcy velocity, even in low permeabilities, given the fact that the polymer, I mean, might have a bit more retention because of maybe the size, just the size or these kind of things, so you think this won't make any difference in terms of resistance factor?
Well, so you get to a point that's good, is the truth is, if you have the laboratory data and really good, realistic, hard laboratory data to support what you're doing, you can justify anything that you're doing. I'm just saying, but as you indicated earlier, most people don't want to pay for lab work. They don't want to do lab work. It takes time, and they just want to go to their simulator and assume whatever the simulator has assumed in there. And some of these simulators I see have unrealistically high resistance factors and unrealistically high residual resistance factors. So that's a flaw with a lot of these simulators right now. So that's why I'm giving this guidance. Your point is, if you have the laboratory data to back it up, that's wonderful. Just you can do whatever you want in that case.
I mean, a bit more than this, because in the papers I read, I don't see many people correcting for the actual velocity in the pores, if it's low perm or high perm, because
yeah, so that's a reasonable point, and again, it gets back to, are you willing to go into the laboratory and measure these things, or are you just going to say, well, look, I don't want to spend any money on laboratory work, and I just want your best projection based on what people have already done in the past? And it depends on where you are with that decision, right?
Yeah. So this point, you say the two categories. So on conventional HPAM, and you said that resistance factor should not be twice more than the viscosity. So this is where
and even that's the most optimistic case. I would say Guillaume's case of it being 30% higher than viscosity is probably, most realistic case. And there's a pessimistic case of just saying, let's assume it's just the viscosity. Yeah. Um,
So, and then the second category was probably the other polymers, then
yeah, so associated polymers are in a separate category, and absolutely yes, you can get far higher resistance factors than indicated by the viscosity. And but that in my mind brings up in a short core, or can I really get that effect to propagate the kind of distances that I see in my reservoir? Because we know associative polymers, what they're doing is they're associating. So they're basically taking small things and making big things out of it. And if it's a big thing that's giving me my high resistance, the concern is that, well, if I've got a small pore that has to go through, maybe it's really not going to go anywhere. Maybe I'm not having any chance of getting that any significant distance into the formation. So if you want to go with associative polymers and that kind of thing, you got to first prove that you can really propagate that effect the distance that you need to in your reservoir.
which correlates to a recent paper you shared about the viscoelasticity also, because it's also a parameter people use in some cases as inputs. And you mentioned also that we should see if the pressure gradients inside the reservoirs allow this effect to happen, like basically also propagating associative polymer. So the issue is the same, which is, can we observe in the field what we see in the lab, and if the conditions are the same? And so associative, as for viscoelasticity, is my, or are my conditions met deep inside the reservoir to allow this phenomena to occur, probably. So
Yeah, no, that's exactly right. And as we were discussing, Madar Zad had just made a presentation in Egypt here a couple of days ago on looking at this. He looked at all these different reservoirs throughout the world: Dacheng, Pelican Lake, Mangala, lots of different places, and he's asking the question: is the velocity or pressure gradient that we see in the reservoir high enough to be consistent with where we see shear thickening or viscoelastic behavior being important in our core floods? And his conclusion is that it's a pretty darn small fraction of the reservoir that's going to see that as a general rule. So maybe we shouldn't be counting on that effect very often. Yeah. Yeah.
so just we switched things, but so we were on resistance factor. So what about residual resistance factor and the inputs people have in their
So
simulation?
that's a good point, and then it really strongly impacts. Everybody wants to inject the minimum polymer that they can. That's just normal economics, right? But the question is, do you have a good justification for it? And as a general rule, the higher if you got, let's say, one permeability, let's say we don't have multiple permeabilities, but just for simplicity right now, let's just say we got one permeability. Um, the ideal thing would be to have the highest residual resistance factor you could. I mean, if you could make your residual resistance factor, which is basically the permeability reduction caused by the polymer, if you could make that the same as the resistance factor, you just inject a very small amount of polymer and you get, you don't have to inject a very large polymer bank, is what that says. But the problem is, if you don't measure your residual resistance factor right, you get a unrealistically high value, and you get an unrealistic projection, especially with respect to the bank size. So I'm going to say something here that is something people don't want to hear, but it's the truth. If you want to have a sustained, successful polymer flood, you need to be injecting the largest practical polymer bank that you can, maybe at least a 50% pore volume bank. Now, I know there's people out there saying, I want to use a 10% or 20% pore volume bank, and that's got some really flawed reasoning with it from both the simulation viewpoint and maybe also from a laboratory viewpoint. From the laboratory viewpoint, like I said, if I truly had a residual resistance factor that was high, I could get away with a small polymer bank. But the truth is, that's usually a laboratory artifact. In my experience, if you're in really floodable permeability, not super low permeability, but floodable permeability, you're never really going to get a residual resistance factor greater than 2, under normal realistic type of conditions. So I know some of these simulators kind of have built in as default, so well, why not use values significantly higher than that? And you're fooling yourself by putting those high values in. So, like I say, the most optimistic case I would say on residual resistance factor is never allow anything greater than 2 in your floodable permeability zones. Probably the conservative case is assume your residual resistance factor is 1, and maybe somewhere in between there are the range of where you really want to have sensitivities. And a big reason why people don't measure residual resistance factors correctly is because they don't put enough throughput into their cores when they're measuring enough water throughput into their cores when they're measuring residual resistance factor. That's also impacts the simulation side of this, because a lot of times, of course, people, when they do their simulations, they'll do sensitivity studies and they'll say, well, I'm going to look at the effect of bank size. But there's a real flaw with that, in that the vast majority of our simulators, maybe all of the simulators, they really don't do a very good job of capturing the severity of water viscous fingering through the polymer bank in the most permeable pathway. They're always super optimistic. They tend to predict more of a piston-like displacement of water displacing polymer solution, and that's never going to happen. So when people do their simulations and they look at sensitivities on bank size, they need to realize they're getting an overly optimistic projection. Okay, that what they really should do when they switch to water injection is basically immediately switch to a much more pessimistic water cut type of curve. Our actual field data says when you start injecting water, you're probably going to get water breakthrough in maybe 2 or 3 hundredths of a pore volume of water injection. That's when you're going to probably see water injection very fast, and that's not captured in these simulators. So that's a key thing, is when you're doing these simulations and you think you're doing sensitivities on bank size, you're giving a very optimistic case. The reality is we need to be injecting the largest practical polymer bank that we can.
No, but so to summarize, also on this issue, the strange part with residual resistance factor, as you mentioned, is if it's very high and we have a small bank, so the question is the mechanism, because I don't see how we can have a very high RRF and propagate anything and push an oil bank. It's going to be stuck. You will lose injectivity very fast and it will not go anywhere, not even the first
Yeah, it's
few
not
10 or
realistic. You're
15
never going to
meters.
really get that in a
No.
reservoir. That's true.
So this is the first part. That's why it's always a bit strange that this argument is still around there, because even from a practical standpoint, it doesn't make any sense. And the second, as you said, is, well, the damages that will be made will still be much lower in the high perm zones compared to the low perm zones, which is where, once again, the water will finger through. And because, as you mentioned, the people who put nice RRF, they have an extra oil bump when they resume water injection after polymer injection, which also, as you mentioned, and as you can see in the literature, if you look in the Middle East case in Kazakhstan, as soon as you switch from polymer to water, it's a question of days, sometimes a couple of weeks before you go back to have water breakthrough again, high water cuts, and it's over. So what would be the approach? Maybe about understanding more the economic limit of when does the extra oil doesn't pay for the injected polymer. Might be better if this parameter can be understood by the simulation aspect, or if it's more flexible approach where you have to look to sit every year with the team following your project and say, is it working? It's not. Is it working? Yes, no, why? And then if it's not working for conformance issue, you fix. If it's working, you just prepare more polymer. And once once you reach the crossing point where basically the oil doesn't pay for the polymer, you say, okay, so maybe the question is it time to stop based on how many pore volumes you have? What is the percentage of pore volume you have injected at that point? No?
Yeah, no, I think that's a really good point. I mean, it basically does boil down to that. The value of what you're producing becomes less than the cost of what you're injecting. You got to stop. But you do bring up another point. Is the real question is why am I at that point? And at some cases, like you implied, if I get really bad polymer breakthrough, there's a couple reasons why I might have really bad polymer breakthrough, early breakthrough, let's say. One is that I simply didn't inject enough high end of polymer concentration of polymer, and I'm just getting, maybe not as bad a viscous fingering if I had injected water, but I'm still getting really bad viscous fingering. And the whole idea of the polymer is get the polymer concentration up to the point where I get rid of viscous fingering. The other possibility is that I've got a fracture-like feature that's gone all the way from my injection well to my production well. And then the key question for you is, should I be continuing this polymer flood, but just correcting that particular problem so that I could get on with my polymer flood? So that's a key decision you have to make.
We mentioned resistance factor, residual resistance factor, so the issue with viscosity curves. What about maybe molecular weights for
Yeah,
various
so
permeability?
for a long time, people have known polymers are really big, and I get the biggest viscosity for my money if I have the biggest polymer, the largest molecular weight polymer. But I know everybody's known for 50 years that there's a limit to that these polymers can become too big to fit through these pores. And the question is, where is that cutoff? Okay, so economically, I want to use the largest polymer I can, but if I can't propagate it through the rock, I'm wasting my time. So I've got to get the polymer size so that it actually will propagate through the porous rock. And the question is, where is that cutoff? And one of the things that I see that's unfortunate that's happened in just the past few years is that right now there's kind of a myth going out. There's a fellow who, maybe one or two people who have made conceptual diagrams of kind of basically it's a plot of molecular weight versus permeability that the polymer would penetrate into. And a really disturbing thing I saw with that is that they basically are saying that 15 million molecular weight polymer is going to start having trouble penetrating into 300 millidarcy rock. Okay. Now, on the good side, the vast majority of our polymer floods so far have had permeability greater than 300 millidarcy, so you could say it's irrelevant. But normally we're pushing to lower and lower permeabilities. And even with some of these high permeability reservoirs, they have lower permeability segments to them that might be down there. And I got to say, it's a nice conceptual diagram, but there's too many people, especially simulators, that are taking that way too literally. Yeah, I mean, it's flat out false. I've looked at cores throughout the world, and I admit it's possible maybe there's a strange lithology somewhere where maybe 15 millidarcy or 15 million Dalton polyacrylamide won't penetrate into 300 millidarcy rock, but I've never seen it. Okay. In fact, I've never seen a case where that kind of molecular weight of polymer, even 18 million molecular weight polymer, won't penetrate into 200 or maybe even 100 millidarcy rock. So that's being way too conservative, and I'm seeing really troubling signs that people are taking this conceptual diagram and pushing it way farther than they need to. Especially, I mean, I saw a simulation presentation where saying that was the cutoff, and that's just false. That's overly
Well,
pessimistic.
one of the reasons why it's probably oversimplistic, even though I mean I think I've seen this diagram, but I don't remember the details. Is penetrating into a pore for a polymer depends on its hydrodynamic volume, which depends on temperature, salinity, chemistry, and everything. So if you want it to penetrate a bit better, either, for instance, you take, I mean, if you have a bit higher salinity, probably even the hydrodynamic volume will be different, and it might just go well into these pores. So I think, yes, these diagrams are way oversimplistic.
Yeah,
And
but let me elaborate on that. I mean, I recently did a study with a couple of other people from UT Austin and from a couple of different places, Kuwait and Saudi Arabia, and we looked at a really broad range of salinity. So from 1,000 parts per million TDS all the way up to pretty darn high 10%, 100,000 part per million TDS, and also with really a broad range of calcium content on it. And you're implying that okay, in a low salinity, the polymer is really expanded, so maybe it's going to have trouble. We have a problem penetrating that into 100 millidarcy rock on any of those circumstances. That's an 18 million molecular weight polymer. So I admit it's possible, but to call that a general rule is flat out false. It's just not true. So
no, but it's always been the quest of people to have a molecular weight distribution versus permeability.
uh-huh.
But in addition to first, there are some we discussed last time some flows in the laboratory, which is polymer solutions are pristine, they have not been degraded, they didn't go through perforations, core floods
Mm-hmm.
that run as fixed rates. So there are a lot of other reasons why basically all these polymers are doing very well when they enter the reservoir, and no one has ever complained, as far as I'm aware of, about this. Plus, again, it comes back to the start of the discussion is, okay, I have an injectivity issue. How do I know is the polymer molecular weight and not the water quality, not my poor understanding of the reservoir, not that I have clay swellings, not I have in internal cake? How can I have a workflow that will tell me, yes, this is the issue that I'm facing, and in this particular case, I have to shear my polymer more so it gets into the lower permeability zone? It's very difficult question, even from a practical standpoint. Because imagine you control everything. It's like my water quality is perfect. Everything is perfect in my well, in my reservoir. It's just, yeah, when I use this polymer, it's not going in. And when I use lower molecular weight, it's going fine inside the rock. And just to finish on
Are we
this
talking
point,
on a laboratory viewpoint or a field
um,
viewpoint?
so both, because for instance, my experience in the lab is the sequence you use to inject polymers in a rock matters. My point is, if you start with one polymer, high viscosity going to lower viscosity, or lower viscosity going to higher viscosity, your pressure profile, stabilization, and things, my experience in the few cases I've made, are different. If you start with one polymer from high concentration down to lower concentration, or low concentration to higher concentration, also the stabilization and the resistance factors sometimes are different. For
Is this
reasons,
in what kind of permeability rock are you
we're
working
talking a
with?
Darcy Bentimer, basically. Bentimer
That
and observe,
high?
yeah, yeah, and
Oh,
observe the
okay.
same things
All right.
in Berry. And also
Okay.
something very strange, this is why I'm saying this, is we used to inject very low polymer concentration, 150 or 200 ppm. And well, it was very difficult to have these low concentrations going through the cores, except if you were starting with 2000 ppm going down to 200. But if you started 200 going to 2000, in the experiences I've made, well, it was not working. So again, there were a few cases like this, maybe more than a few, for reasons which are still unclear for me. But so to come back to this point, there are the way people do sequences in the lab, especially when they want to assess impact of molecular weight, concentration, and rates. The sequence has an impact. I think this is the only thing I have to say is the sequence has an impact.
Interesting. Okay.
And
Um,
and
you know,
just to finish
yeah, go ahead.
on your points, I see more and more people, especially now that we are moving into carbonates and lower permeability carbonates. So people want to shear the polymer. They want to pre-shear the polymer in valves to make sure that it will go inside the low permeability zones. Of course, this was designed in the lab, which is with all the topics we discussed before, which is in the lab when you go with the sequence they are using through the rocks of permeabilities similar to the ones in the reservoir, then the conclusion is, well, we have to shear a little bit to get this inside these low permeability rocks. So that's a trend also I see more and more is like we shear to be sure that the polymer will go inside the low permeability zones. So the idea behind this is, I think, reasonable in the sense that, well, if it's very low, very, very low perm, the question is, how do you make sure that you don't have any problem? It's okay, it's fine. It's a good, it's an interesting de-risking strategy. The issue I might see with that personally is that the polymer or the problem that's causing injectivity issues very often are the highest or the biggest molecule into the distribution very often. What I mean is if you, for instance, cut the the long molecules, so the highest molecular weight molecules, then the resistance factor will change dramatically, and you will have less of an injectivity issue. And very very often, this is what you have when it goes through the pumps and the perforations. So my point is that it's already happening. So you're already shearing, everyone is already shearing a little bit the polymer in the perforations, in the pumps, in the pipes, maybe, and not much, which is of course not what you want, but that's way enough to remove the possible problems that very often are caused by the longest molecule. So I don't know if you what your thoughts about all
So
these things.
I think we're thinking along the same lines. You know, and it goes back, it basically boils down to different manufacturers have different degrees of purity on their polymer. And that's maybe not only with respect to just crap that's not polymer in there. I mean, that's one issue. But the other issue is just the nature of the polymer molecular weight distribution itself. And as you said, there are certainly cases where you have a polymer that maybe two polymers basically give the same viscosity to them. But if you could look at the molecular weight distribution, you'd find that one of them had a super high molecular weight type of tail to it. And what the IFP folks a long time ago would call microgels. They're just, you know, kind of stuck together bits of polymer that cause these overly high residual resistance factors, cause these overly high resistance factors, and it can cause plugging and actual plating onto the surface. And what we've seen by experience is that some degree of shearing destroys that, and some degree of propagation through porous rock eliminate that either by filtration or adsorption. So yeah, I absolutely agree. It's good to get rid of that fraction somehow. Um, you know, in shearing, I guess I would say I would be cautious about the degree of shearing. I mean, on the one hand, you want to get rid of that super high molecular weight species that's causing this plugging and this undesirable effect. But on the other hand, you don't really want to be losing too much of your viscosity. So there's a balance point in there that I think people need to
Yeah.
be looking for.
But for carbonates, it's really about really degrading very much all the molecular, I mean, all the molecules to go to,
Well, in
yeah,
that
kind of.
case, I accept that we are kind of in new territory with carbonates, and there's a lot of additional work that needs to be done. But I think the question would be, um, wouldn't it be easier just to have the manufacturer polymerize this to a lower degree of polymerization? So you get
Well,
more and more what you
I
want.
mean, you already have a very low molecular weight. So, I mean, typically what people use, I've been using, as you were mentioning, because we worked in high perm reservoirs, sandstone, very often heavy oil. We're talking multi-Darcy reservoirs. So again, in everyone's mind, you could use the highest molecular weight, so 18 million up to 30, 35 million Daltons for what we call a post-hydrolyzed polymer. But so it's very recent that we start to see people going in the range of 1 to 3 million Dalton, which still remains as powder form, because the problem when you go below the million Dalton, it's way more difficult to have powder. You are going for more, I would say, liquids or beads, which is not very convenient for onshore applications because you will lose active. It would be a bit more expensive. And so the idea is, even for the lowest molecular weights, what people want to do when they think it's still too high is to shear more these low molecular weights to really go low into the distribution and make sure that they enter the reservoir. And the paper I've published last year in the Netherlands, I was analyzing some results from the lab from our company, and what we see is, I mean, even the procedure you use to prepare the polymer has an impact. So if you use a mechanical or magnetic stirrer, then the viscosity will not be the same. If you use a filter 5 microns and 1.2 microns, the resulting, I would say, resistance factor once you inject in the core will not be the same. So for the filter, it's kind of expected, I would say, maybe not that to that extent. But when it comes to preparation of the polymer, like what kind of stirrer you use, for instance, this is very interesting because it means that, well, if you're not aware what you're measuring in the core, in the lab, and everywhere else, I mean, I don't say you're wrong, but you are wrong. The problem is you're still not as wrong as you would be in the field, because the solution you would prepare in the field will also be different than the one you have in the lab. So it's a kind of difficult problem where do we start? So I think it would be probably good to compare polymer in the lab to find the one which, relatively to others, is giving the best everything. So lowest retention, good propagation, good resistance factors, knowing that even if you have some degradation, it will still be the polymer that gives the best results. And then in the field, of course, you do as much as you can. You clean the perforations, you enhance everything, you avoid oxygen, iron, any kind of degrading pump, and these kind of things. But so my point is, everything we do in the lab, we do with a polymer which is will be different than the one in the field, because the batch will be different. The origin might be a bit different, though of course it's standardized and you have quality control and these kind of things. But then the water will be different, the preparation will be different, the equipment for injection will be different. And so my point is, well, so what are we doing with these differences? And today people, nothing, which probably is fine because there might not be much to do. But the point is, we have to be careful to understand how representative all the things we do with the polymer we have in the facilities we have, especially when it comes to measuring molecular weights, viscosity, etc. Because there are differences, nice differences, I would say, substantial differences between the lab and the field. And that's why also in the end, when you come back to simulation, well, they can't be very predictive of anything. Because first, many people don't understand the inputs. The mathematics are a black box. The reservoir is poorly understood, and the polymer is not the same. So, so my question now is, where do we start? Because as you mentioned in the very beginning of the presentation, is Well, injectivity is paramount because if we can't build the business case and predict how much we will get, what's the point of using the models?
Yeah, so I mean, you raised a really good point that we have to make sure that the laboratory work that we do is representative of what's going to be in the field. And a key part of that, if we've got a radically different polymer in the field than we're testing in the laboratory, of course, we're going to be way off base on the thing. So I guess we need to be asking that kind of question. I mean, when we do our laboratory studies, actually get field samples of the polymer to be working with, number one. Number two, when we have make measurements in the laboratory or in the field, like a field viscosity measurement or field injectivity observations, whatever, we need to be having that communication between the lab and the field guy of saying, look, I'm not seeing what you're seeing, and why is that? And let's try to figure that out. And what's the right answer? Is it shearing? Is it ordering a different polymer? Is it doing things differently in the field with how we mix it? Those are questions you have to be on top of. So that's a really good point. Yeah.
Um, well, something we didn't address maybe is retention in
Mhm.
simulations.
Yeah.
So what's your view on this precise parameter?
Well, so I suppose relative to some of the other things, I mean, a lot of the simulations, I've seen a lot of real screw ups that, again, our goal with the simulator or laboratory work, any of them, any tool that we use, we want to reduce the uncertainties. We want to get as many things right as we can. And the whole purpose, as I saw it, of this discussion is in the simulations to try to get correct some of the myths that are out there and get as many things right as we can. Now on retention, uh, probably the screw ups in the simulation are not as bad as with respect to retention as these other things that we've discussed, and not as impactful. But still, it can be important. Simulation handles retention in a certain way, and I guess the first point, maybe most important point, is retention. If it's a low enough value, it's just not of concern. But if it's high, then it's a major concern, and it has a super major effect on economics and performance of the polymer flood. So there it gets back to really having somebody go to the laboratory with that rock and those conditions and say, look, we need to do a realistic retention test and find out what it is. And that, I guess I'd say that's the biggest flaw of somebody who just wants to grab a simulator and throw in whatever numbers they want. That's another area where it's smarter to say, look, let's spend a little bit of money and find out what the retention really is and put the real performance values of the retention into the simulator. If it's low, that's wonderful. Then we don't worry about it. If it's high, then we got to be concerned and we've got to maybe go to a different polymer or do something different. But the key thing there is just measure it. From our recent publications that we've seen some unusual things on the shapes of the
The
polymer breakout
the
curves.
tailing
And
phenomenon. Yeah.
yeah, at Milne Point, where we have illite, a lot of clays present. So we're going to see that if we got a lot of clays present. Maybe we're not going to see it if we don't have clays present, if we're working in carbonates, for example. So it does depend on, and it's very sensitive to divalent ion content, calcium or magnesium content. It's very sensitive to the amount of ATBS you have in the polymer. So, we're not able to predict any of that stuff right now. It really does boil down to, for your conditions, take your polymer, have somebody go into the lab and actually measure this stuff and get a right parameter for you so you can put that into your simulator. That's probably the key message I would have for the simulations. Don't just assume something, go have somebody measure something.
And so one of the parameter which is probably linked maybe indirectly with retention is inaccessible pore volume. So
Yeah,
what's
so I mean that's an active area of discussion for us. You know, if you look at some of the videos and what the simulators do, they actually come out and say this. Well, I just use inaccessible pore volume, or what they call accessible pore volume, kind of the one minus inaccessible pore volume. They just use that as an adjustable parameter, and I don't really see the point of doing that. I mean, if you want to put in an adjustable parameter, call it something else. Don't call it inaccessible pore volume. Put in accessible pore volume, and or put in your adjustable parameter and call it, you know, the simulation fudge factor if you want. But inaccessible pore volume, in my mind, if you've got rock greater than 200 millidarcies, you don't have any inaccessible pore volume unless you've got something really unusual going on there. Carbonates, real low permeability carbonates, yeah, I'm sure you do have an inaccessible pore volume, but the higher permeability stuff, you know, if you're going to put in a fudge factor, call it something else. That's the
means
way I see
yeah,
it.
the fudge I like because it means that if you think you have everything else right, including geology, and you still don't match, and then you put the fudge factor and it works, then it was the fudge factor. So but it means you need to have
Yeah,
everything else right.
and that's the whole point of this whole exercise is let's get as many things right as we can. And
Mhm.
then when we see discrepancies between the predictions or the laboratory work and what's happening in the field, then we try to figure out what's going on and see if we can improve it or not, right? But the thing is not resorting to black magic where we don't need to resort to black magic. There are certain things that we know. Let's get them right and put them into the simulator and put them into our assumptions correctly. And then when we look for unusual things, at least we're going into we increase the probability that we can correct the problem as opposed to, you know, doing something that doesn't make any sense. So
So
yeah.
maybe to wrap up a little bit, so if you had to start by giving um, some advice to people for running simulations for Polymer, what would these how would
So
them look like?
number one, especially in vertical wells, the simulators we have simply can't predict injectivity. So don't pretend that you can, and don't make projections about saying, well, I'm going to justify injecting a really low polymer concentration because of some artificial injectivity concern. Don't pretend you can predict injectivity with a simulator in a vertical well. In a horizontal well, maybe, but not in a vertical well. You just, most of these people are just fooling themselves with that. Number two, um, realize when you do sensitivity studies on bank size, you're fooling yourself. Uh, these simulators don't do a good job of predicting the severity of water fingering through the viscous polymer bank that's ahead of it. So you're going to get an optimistic case. What we really want to do is we want to inject the largest practical polymer bank that we can. Three, actually measure your relative permeability curves. And that's why I suggested this SPE 190321 for polymer flood to try to get you in the right spot. And the polymer flood, it's most important economically that you get about the right polymer viscosity that you're injecting, right? And the only way to do that is with a little bit of laboratory work. Same thing with polymer retention. Don't just assume it. Go have somebody measure it in a decent way. Okay, so those are the top things. You know, we also talked about residual resistance factors and resistance factors. You know, the simulators have, as a general rule, put in too high of values for those. In my mind, you should never put in a residual resistance factor greater than 2, and you should never have your resistance factor greater than 2 times your viscosity. And I think Guillaume's suggestion of what we really observe is that the resistance factor is about 1.3 times greater than viscosities, probably a really good place to start. So those are some of the key things. These one other thing I do want to mention is just right now, again, some guy is out there showing this conceptual curve on the cutoff between molecular weight and polymer molecular weight and permeability. And that's just not quantitative. They're saying that 15 million Dalton polyacrylamide won't go into 300 millidarcy rock. That's just wrong. You might have qualitatively the right answer, but where you put that curve is just wrong. So I'd say those are the key things to take away from all of this.
So maybe emphasize a few things based on what I've seen also. So as you mentioned, I've never seen anyone being able to predict injectivity correctly with any of the 3D simulators. There have been exceptions, but I think it's been more luck than I would say,
Agreed. Yeah,
engineering.
absolutely. Yeah.
So the reasons behind that is, but first, I think the reservoir model, geological model, is probably not the best, which is normal because we don't have enough data to populate the model. But we have to remember that when we start modeling, which is if we have a very large grid cells, 100 meters to 100 meters, then we should not expect to have a very fine response when we start polymer injection. So there is a reservoir part, which probably is one of the big black box and problem, which is, well, if we don't know the geology, we will never get anything right anyways, whatever technique we use. Then for polymer, I think there was a discussion about this, the Pieceman model that was used for non-Newtonian fluid that was wrong. There was a paper about this from Tay and McGrich and Giddens from Imperial College. So there were some mathematics which I think were not appropriate. Maybe there has been some remediation, but it's unclear. I think the equations are very, very complex, and there are so many parameters that, as you mentioned, if you don't get all of them right by measuring things correctly without any problem and bias in the lab, it will be very difficult to understand which one to change when nothing is matching your expectations. Injectivity, as I said, was never predicted. And if you don't benchmark the model with actual field results, and there are many now, it's not an excuse to say, well, but it's not exactly my reservoir. Well, it's never going to be, but I think the reservoir engineering principles are apply in all reservoirs.
Yep.
So I think it should be benchmarked properly. Then try to predict maybe pressure drop in core floods, if you can, just to see how wrong the simulation is and the mathematics and your understanding to see if it can be tweaked before upscaling. For parameters, avoid viscosity versus concentration curves. Go for resistance factor curves if you can use them as inputs in your model. So resistance versus velocity. What else? Yeah, shear thinning. If you know your shear rates in the well and reservoir, why not? Shear thickening, well, avoid even to study it. If you perforate or fracture, you will have no problem with shear thickening. So, and you can also play on rates or whatever. So if you can avoid studying shear thickening, please do so. And for the rest, I will just repeat what you said, which is a residual resistance factor. Well, the water will always finger through the relperm zone anyways afterwards. So, you can you can tweak things around, but the surprise of seeing water coming again very, very fast after stopping polymer injection will just tell you that, well, this is what happened. And for bank size, I think a topic which would be very interesting to discuss another time is what we touched upon a little bit, which is when we have early polymer breakthrough, or when we have polymer breakthrough, is it because the project is over, or is it because there is something we have to fix?
Yes, good point. Right.
And also the question is, can we understand if it's something we have to fix? What is the type of problem we have to fix, and how can we fix it knowing that now we have something which is more viscous in our reservoir. And so the mobility contrast between what we will inject after and after the polymer to fix the polymer problem will also be impacting our design, the choice of technology, and everything like this. So
Yeah, and to be a little bit optimistic, there certainly are cases where we can make fixes, and we can elaborate on that at another time here. So
yeah.
yeah,
Anything else you would like to
well, good
mention
start
or?
for now here. That's great. Good discussion.
Well, thank you very much once again, Randy, and we'll see you next time to discuss on another topic.
All right, thanks a lot,
Bye
Antoine.
bye. Thank you. Take care.